66 million years ago, the sky above what is now Mexico caught fire. Not slowly, not like a sunrise. All at once, a column of molten rock punched through the atmosphere, and material that had been sitting inside the Earth's crust for hundreds of millions of years was now in space. Below, the ground had already begun to move, not in hours, in seconds. The age of dinosaurs didn't end with a bad year, or a cold snap, or a slow decline. It ended in a single morning. And we know with extraordinary precision what that morning looked like. This is what happened, hour by hour. The impactor. The object that ended the Cretaceous period was roughly 10 kilometers wide. To put that in your hand, stack Mount Everest on top of itself. That's about the width of what hit. It wasn't moving like a falling rock. It was moving at 20 kilometers per second, 58 times the speed of sound. Astronomers classify it as a carbonaceous chondrite asteroid, dark, carbon-rich, originally formed beyond Jupiter's orbit in the outer solar system. At some point, millions of years before impact, a gravitational nudge sent it inward, toward us. There is a minority of researchers who have argued it may have been a comet. That debate is ongoing, but the consensus points firmly to asteroid. The angle of entry mattered. It struck at between 45 and 60 degrees to the surface, not a direct vertical plunge, not a glancing blow, a perfect, catastrophic middle ground. And the location it chose to hit was, in the worst possible way, unlucky. The seafloor of what is now Mexico's Yucatan Peninsula was saturated with gypsum, a sulfur-rich mineral. That detail will matter later. First minute. The asteroid hits the shallow carbonate shelf of the Yucatan. The impact lasts less than a second. In that moment, it releases the energy equivalent of 100 teratons of TNT. That's 4.5 billion times the explosive power of Hiroshima. Some models say 10 billion. The models don't entirely agree on the number. They agree on the scale. Nothing in recorded human history comes close. The first thing that happens is that a cavity opens in the Earth, 100 kilometers wide, 30 kilometers deep. It punches straight through the crust. Then the crust collapses back. The center of the crater rebounds. A peak ring forms, like a splash frozen in stone. If you've ever dropped a pebble in still water and watched that crown of water rise and fall, you've seen a version of what happened here, only in rock, and over seconds, and over 100 kilometers. This same peak ring was drilled by scientists from the International Ocean Discovery Program in 2016. The core samples they pulled up contained granites that were originally 12 kilometers below the surface. The impact brought them up. 25 trillion metric tons of molten and vaporized rock shoots upward through the atmosphere. Some of it leaves Earth's gravity entirely and enters orbit. Some comes back. We'll get to that. The plume itself reaches temperatures several times hotter than the surface of the sun. The surface of the sun. Not a metaphor, a measurement. The first 6 minutes. 3,000 kilometers to the north, roughly where the Dakotas sit today, it is a spring morning. The inland sea that bisects North America is calm. Paddlefish and sturgeon push upstream. A triceratops moves through a tree line. The sky is blue. Then the ground shakes. Seismic waves travel through rock at roughly 5 kilometers per second. 6 minutes after impact, they reach the Hell Creek region of what is now North Dakota. The earthquake that arrives is somewhere between magnitude 10 and 11.5, beyond anything in the modern instrumental record. The inland sea responds to liquid responds to any container under seismic stress. It sloshes. Scientists call this a seiche. Think of water moving in a bathtub during an earthquake, amplified across hundreds of kilometers of shallow sea. The surge that follows isn't a tsunami. Here's why that distinction matters. A tsunami traveling from the Yucatan to North Dakota would take somewhere between 17 and 20 hours. We'll show you why that timeline rules it out. What buries the Hell Creek region in the next few minutes is seismically generated, local, and immediate. The surge is at least 10 meters high. It carries everything in its path, fish, trees, sediment, and dumps it in a tangled mass. In about 15 minutes, it is over. What remains is a deposit that will sit undisturbed for 66 million years. Taunus, the clock frozen in stone. In 2008, a field paleontologist named Rob Sula and a University of North Georgia professor named Steve Nicholas found something unusual in the Hell Creek Formation of southwestern North Dakota. They called in a graduate student from the University of Kansas named Robert DePalma. DePalma spent 4 years excavating in near total secrecy. What he found and what his team published in the Proceedings of the National Academy of Sciences in April 2019 is unlike anything in the paleontological record. The site is Taunus. In geology, a few centimeters of rock typically represents a few thousand years of sediment accumulation. In Taunus, the team found a layer 130 meters thick, deposited in a single day, the highest rate of sediment accumulation ever documented in the geological record. Inside that layer, hundreds of fish, not 3 or 4. Previous Hell Creek Formation excavations had yielded 3 or 4 complete specimens total. Taunus produced hundreds, representing multiple species, some still unnamed. But the fish aren't the story, they're the timestamp. Inside the gills of the paddlefish, the team found spherules, tiny glass beads, roughly a millimeter across. These are tektites, droplets of molten rock that were launched into the upper atmosphere by the Chicxulub impact, cooled into glass as they fell back to Earth and rained down across the continent. Paddlefish feed by swimming with their mouths open, filtering water. The only way tektites enter a paddlefish is if that paddlefish was alive and swimming in the river when the tektites were falling from the sky. The tektites are chemically matched to Chicxulub ejecta. The fish was alive during the bombardment. Physics calculations show that ejecta from an impact the size of Chicxulub would reach a location 3,000 kilometers away in somewhere between 13 minutes and 2 hours. The fish was still breathing. The rain of glass. Across the planet, the ejecta cloud is doing something that sounds like physics fiction, but is verified by sediment records on every continent. Droplets of molten rock, the same material that just obliterated a 50-kilometer deep section of Earth's crust, are now in the upper atmosphere. As they cool during descent, they form perfect glass spheres, millions of them, billions of them, falling everywhere. In Taunus, fish are still swimming in the Seiche surge when the glass arrives. The tektites found in Taunus still have unaltered glassy cores, meaning they cooled fast enough and buried fast enough to survive 66 million years without dissolving. Their chemical signature matches the Chicxulub crater exactly. Here is what this means for the fossil record. Taunus is not just a mass death site, it's a forensic scene with its own clock. The tektites tell us when relative to the impact. The fish gills tell us the animals were alive when the glass fell. The Seiche layer beneath tells us the sequence. The pollen and fish bone rings tell us the season. We know when, we know how, we know what the weather was like.
The season of impact. This is one of the stranger scientific outcomes of the last few years. 2 independent research teams, one led by Melanie During at Uppsala University in Sweden, published in Nature in February 2022, one led by DePalma and published in Scientific Reports in December 2021, both reached the same conclusion using different methods. The asteroid hit in spring, Northern Hemisphere spring. During's team read the growth bands in fossilized paddlefish and sturgeon bones recovered from Taunus, the same rings that trees use to record seasonal growth. The carbon isotope signals stored in those bands told them the fish were in an active feeding phase consistent with late spring, not yet at the peak of summer feeding. DePalma's team used pollen, insect damage patterns on fossilized leaves, adult mayfly fossils, and trace metal analysis to reach the same conclusion. Spring in the northern hemisphere is autumn in the southern hemisphere. That asymmetry, some researchers now believe, shaped which species survived and which did not. Animals in the north were active, breeding, feeding, fully exposed. Animals in the south were preparing for winter, lower metabolic rates, some beginning dormancy, food stores already established. The planet did not experience the impact equally. The thermal pulse, T plus 30 minutes. Here's where the science gets genuinely brutal. Superheated winds, moving at over 1,000 kilometers per hour, radiate outward from the impact zone. Within the first few hundred kilometers, they shred vegetation and kill anything exposed. Simultaneously, the ejecta cloud is re-entering the atmosphere. As billions of glassy particles descend through the stratosphere and upper atmosphere, they heat it. Friction converts kinetic energy to thermal radiation. This isn't localized, it's happening across the entire sky that's receiving falling ejecta. Studies estimate that thermal radiation from the re-entering ejecta was sufficient to ignite dry vegetation at sites up to 1,500 kilometers from the crater. Here is an important revision to an older claim. For decades, the standard model held that this re-entry event triggered an instantaneous global firestorm, that the entire Earth's surface was broiled from above simultaneously. That version has been revised. What actually happened was regional, not global. Southern North America burned. Areas directly exposed to the ejecta plume burned, but instantaneous worldwide ignition is not supported by the current evidence. The soot found in boundary sediments appears to come partly from the organic carbon in the target rock itself, not solely from burning forests. The planet wasn't set on fire everywhere at once. It was set on fire in the worst places first. The tsunami, T plus hours to 1 day. While the Seiche hit North Dakota in minutes, the actual oceanic tsunamis generated by the Chicxulub impact took much longer to propagate. The initial displacement wave near the impact site reached an estimated 1.5 kilometers in height. That's nearly twice the height of the Burj Khalifa, the tallest building on Earth, as a wave. Subsequent tsunamis in the range of 50 to 150 meters traveled outward across the Gulf of Mexico and beyond. Sediment records in Texas and Florida preserve the evidence. Meters of debris deposited in hours, carrying material from the impact zone hundreds of miles inland. An estimated 48,000 cubic miles of sediment moved across the Gulf of Mexico in that window. By the end of the first day, large sections of what is now the American Southeast are buried under impact debris and marine sediment. What the crater tells us. Inside the crater itself, the record is extraordinary. When the International Ocean Discovery Program drilled into the Chicxulub Peak Ring in 2016, they recovered a core sequence that tells the story of the impact day in unprecedented detail. At the base of the post-impact section, a thick layer of impact melt and shocked rock, recording the instant of collision and the first minutes. Above that, a coarse-grained tsunami deposit dumped as the water surged back into the crater. Above that, charcoal, burned wood fragments swept in by the receding waters. The landscape around the crater had already burned by the time the water came back. Above that, fine-grained sediment settling slowly from the water column as the tsunami dissipated. 1 day's worth of geology, 130 meters of it, sitting on top of a world that below that line is entirely Cretaceous. Above the line, not a single non-avian dinosaur, not one. Who survived and why? Not everything died. That matters as much as what did. Birds survived. the descendants of theropod dinosaurs, specifically those small enough to shelter, diverse enough in diet, and capable of surviving on seeds and insects when the food chain collapsed. Mammals survived, small, burrowing, generalist feeders. Crocodilians survived, turtles, snakes, some fish. The pattern is not random. Animals that could go underground, endure cold, eat almost anything, and reproduce quickly had the best odds. The largest animals, anything that required significant daily caloric intake, collapsed within the first years as the food chain buckled. Without sunlight, photosynthesis slowed. Without plant growth, herbivores starved. Without herbivores, large carnivores followed. Here is where the science surprises. A 2026 study led by Chris Lowry at the University of Texas Institute of Geophysics, published in Geology, found that new species of plankton appeared fewer than 2,000 years after the impact. Between 10 and 20 new species of foraminifera, tiny shelled marine organisms that form the base of the ocean food chain, emerged within approximately 6,000 years. The previous assumption was that recovery took tens of thousands of years to begin. The new evidence suggests it started within 2,000 years after the impact. Life didn't pause, it adapted immediately relative to geological time. What remains unknown? Not everything is settled. Here is what scientists are still working out. The exact trajectory of the impactor is not confirmed. The angle range of 45 to 60 degrees is modeled, not measured. That angle changes the distribution of thermal effects and ejecta. It may explain certain regional fire patterns and why some areas show more impact soot than others. The role of the Deccan Traps, a massive volcanic province in what is now India that was erupting heavily around the same time, is genuinely contested. Some researchers argued dinosaur populations were already under stress before the impact. The Tanis evidence, including a partial Triceratops and the depth of the Tanis assemblage, suggests that at least North American dinosaur populations were thriving at the moment of impact. But whether global populations were in decline is not resolved. A 2025 study suggested the Chicxulub impact may have altered the movement of tectonic plates in the Caribbean region. That claim is preliminary and awaits broader validation. And there is one detail from De Palma's Tanis excavation that remains without independent confirmation. The suggestion that some tektites preserved in amber at the site may contain intact atmosphere from 66 million years ago. If true, it would offer a direct chemical window into the Cretaceous sky. That claim has not yet been verified by a separate research group with independent access to the samples. Access is the constraint. De Palma holds the excavation lease. The site has not been opened to independent teams in the way that would allow full verification. The 2019 PNAS paper passed peer review, and its core findings are broadly accepted. But some of the more extraordinary individual claims from Tanis are still waiting for the second set of eyes that science requires.
66 million years ago, on a spring morning in the northern hemisphere, the sky above Mexico turned white. In 13 minutes, glass was falling in North Dakota. In hours, the entire globe was wrapped in a stratospheric shell of debris. By the end of the day, the food chain that had sustained life on Earth for over 150 million years was already collapsing from the bottom up. The non-avian dinosaurs didn't die that day. They died over the weeks and months and years that followed, as the sun dimmed and the plants failed and the prey disappeared. The impact day was just the moment the door closed. What we know about that day comes from a 130-meter column of sediment in a North Dakota field, from drill cores pulled out of a buried Mexican crater, from fish gills packed with glass, and from 66-million-year-old isotopes locked in bone. The Earth kept a record of the worst day in its history. We've spent the last 40 years learning to read it.